Welcome back from break, everyone. Welcome to a wild Wednesday, and thank you for showing up for your learning. I know that the morning dragged a lot and did not go the way I planned, or perhaps you envisioned when you came into class, but here we are. Let's take a look at the new content for today, which is getting started on some exponential functions. I will just take one brief moment, though, to point out something in the D2L. For those that are interested in the Unit 1 Delta Math Club to recoup some marks from the Unit 1 test, you come into Unit 1, you go down all the way to the bottom, and there's a Unit 1 Functions Club review here of me going through the various Delta Math problems and giving you walkthroughs on how to do those. I definitely encourage you to use this as part of your process whenever you get stuck, because it's the relearning of that content that maybe you got and didn't quite capture, or maybe never captured. That's the main goal, is to get you those skills so you're ready for grade 12. So that's why I'm producing these videos for you. Okay, so for today, I wanted to start by just very briefly introducing the idea of an exponential function. You will see these inside the Delta Math today. There will be some transformations of functions, and they'll assume you know about exponential functions like these. So let's first build out a table of values and then explore what this function is going to look like. So if I have a function that looks like this, f of x is equal to 2 raised to the power x. Now we have a new type of function here. This is different than a quadratic. It is not x squared. It's now 2 raised to the power x. When those two flip positions, very different. So let's take a look at when you have something like x is 1. Well, we're going to look at 0. We're going to look at 1, 2, 3, and 4. And then we're going to build this out visually. So what's my y value going to be if I have 2 to the 1? 2. Yeah, and then how about down here? 2 to the 2? 4. 2 to the 3? 8. 2 to the 4? 16. Okay, how about 2 to the 0?
1.
Someone else. 2 to the 0?
0.
2 to the 0. Sander? 0. Yeah. See, Siraj, there's some confusion here.
2 to the 0 is 1.
Dave, what is it? 1. What if I had 1,057,000 to the 0?
1.
What if I had negative 5,000 to the 0?
1.
There's always 1. This is 1 here. Okay, so let's plot some of our points. So we have here, oops. Oh no, what am I doing? Okay, I have to go this way. Oh, watch Mr. Jennings as he struggles with the technology. Oh, there we go. All right, so now let's plot some of our points. We have, here we go. When x was 1, we had 2. So there's the point 1, 2. Here is the point 2, 4. Here is the point 3, 8. And then the point 4, 16 would be, well, it would be somewhere up there. Okay? And then we had the point 0, 1. Anything raised to a 0 exponent, 2 to the 0, gives us 1. So that's that there. This function actually comes in through here. And we'll take a look at the negative x values in just a moment when we review our exponent laws. But these functions look something like this, and they grow very, very quickly. Okay, I hear a lot of chatter in the back, and so I'm going to ask a question of the people in the back of the room. Do you like money? Yeah. Do you want to understand how money works a little better? Yeah. Have you heard the expression, time is money? Do you know why that's true mathematically? Sure. Okay.
Inflation.
You're going to get, yeah, well, inflation is one thing that's happening to money. Inflation over time, the value of money goes down. When I was your age, I could buy a chocolate bar for $1. No, you can't buy a chocolate bar for $1. This type of stuff. Now, people are looking at me like, you're that old, you could buy a chocolate bar for $1? Yeah, and gas was like 40 cents a liter and stuff like that. So anyway, yep.
We can buy chocolate bars for $1.
I know you still can. I know. That's why I'm joking. I'm not that much older than all of you. Okay, so now, whoa, I used that as a ploy to get your attention, and now you're chattering again. Come back to class. I'll wait. Hey, Brody. That's the depreciation. All of these things are functions. They all work exponentially. So understanding this unit of study is going to help you understand all of these topics. So let's take a look at this unit of study. In order to really go into these functions and understand particularly what's happening in the negative values of x and what's happening in between the points where x is not an integer. What's the domain of x here? Is it real numbers or is it integers? Yeah, it's real numbers. I drew a solid curve through all of these points. That means I need to know if I raise 2 to the power 1/2, I need to know what's happening. Or if I raise 2 to the power 5/3. Have people ever thought of this? Exponents that are fractions? Yeah, it's allowed, and we're going to learn about that tomorrow. But for today, let's review our basic exponent laws. Okay, so our basic exponent laws, we will find them in here. So let's take a look. We have the base of the exponent. We were just looking at the function f of x is equal to 2 to the x. So x was now the exponent. Our variable is the exponent in exponential functions. And we need to look at the multiplication law, the division law, power to a power law, the zero exponent law, and negative exponents. This is what we're going to look at today. Tomorrow we will look at fractional exponents, rational exponents. Okay, so let's take a look. When we're multiplying exponents with the same base, people remember what we do. X squared times x to the 3 gives us x to the 5. How did we get x to the 5? Added what, Rylan? Yeah, we add the exponents. So I'm going to give you an example. You're going to solve it for me. If I have a to the 6 and I multiply that by a to the 27, what does that give me? a to the 33. Very good. So you're going to want to remember this and write it down. If I have x and I raise that to the power a and I multiply that by x and I raise that to the power b, what's that going to give me? X to the what kind of ab? How do I not do that anymore? There we go. X to the ab? No, it's not ab. What is it? Yeah, this is x to the a plus b. Yeah, that's what that is there. X to the a plus b. So that's my general rule that I want to remember. That's always going to solve these problems for me. Now, let's take a look at another rule. If we are dividing, and this is an ugly way of writing it. I much prefer if we write this x to the 5 over x to the 3, but that's what this is. This is x to the 2. How do we do these division problems? Yeah, I subtract the exponents. So let's take a look at why that is. If I have something like x to the 5 over x to the 3, what can I do if I forget this law on the test? Suraj, you got some ideas? I just expand it. That's great, Suraj. So I have x times x times x times x times x. And then this is all over x times x times x. So this is x to the 5 over x to the 3. Then I can go ahead and do some canceling, right? This x cancels that x. This x cancels that x. This x cancels that x. This is why we're doing subtraction here when we do our exponents like this. And that leaves me x squared. Great. But what if I have something like, and we're going to go a little bit ahead here. What if I have a problem like this? X squared divided by x to the 3. What does that give me? Dave? X to the negative 1. How do I do a negative exponent here? Sorry, you just put it in the calculator. Yeah. What's this equivalent to? If I wanted to write this without an exponent. Suraj,
1 over x.
this is equal to 1 over x. The negative sends this to the bottom of a fraction. Here, let's expand this out. This is equal to x times x. This is x squared over x cubed. X times x times x. If I do my canceling here, I will cancel this x, cancel that x, cancel that x, cancel that x. That leaves 1 on the top over x. So x to the negative 1, x to the negative 1 is another way of saying 1 over x. All this negative does, all that negative does is it sends the base to the bottom. So here's another related question. If I had x to the negative 5, go away. What is this equal to? X to the negative 5 is equal to what? How would I do that? How would I write that with a positive exponent? So this negative, it has a habit of sending the whole thing to the bottom of a fraction. So, Suraj, what will I have?
1 over x to the power of 5.
1 over x to the power 5. So the negative just sends it down to the bottom. 1 over x to the power 5. I could create this with a problem like this. X to the 2 divided by x to the 7. That would give me x to the 2 minus 7. That would give me x to the negative 5. If I expand this one, I would have 2 x's multiplying each other on the top and 7 x's multiplying each other on the bottom. After my cancellations, I'll end up with 5 x's on the bottom. The negative just sends this down to the bottom of a fraction. So dividing, we can remember, if we remember our division law, that x to the 5 over x to the 3 is equal to x to the 5 minus 3, we can use that to remember what a negative exponent is going to do to our calculations. Now, let's take a look at powers of a power. When we're raising powers to other powers, we are going to multiply now the exponents. So let's take a look at some examples. If we have x squared all raised to the power 4, we have x to the 2 times 4, which is x to the 8. 2x squared raised to the power 5. Oh, why did this change to 32x to the 10? Ryan.
Sorry, can you just go through the slides a bit slower? Like I'm just trying to write down the
Okay, sure. Yeah. So I will also put this PowerPoint into the D2L for us at the end of the lecture. So because that's really great. Thanks. Here, one thing I can do if I get confused about these is write them out as a series of multiplication. I'm not going to do this example because it's going to be a lot of writing, but let's take a look over here. If I have now a problem like, let's use black, let's blue, I like blue. Let's look at 3x squared raised to the power 3. Write this one out as a repeated multiplication. We would have 3x squared multiplied by itself 3 times. So now to solve this one, I multiply all the coefficients. So that would give me 3 multiplied by itself 3 times. And then I multiply x squared times x squared. What do I do when I'm multiplying the powers with the same base? Suraj?
You add them.
I add the exponents. So here I would have x to the 2 plus 2 plus 2. So that would be x to the 6. I could have gotten there with my power of a power rule here, because I can always just take a look at these numbers and multiply those numbers. 2 times 3 would have given me 6 here. But I can also write it out as a repeated multiplication and add. Or I can multiply here. Adding would give me 2 plus 2 plus 2 is 6. But adding something repeatedly is the same thing as multiplying. But I also need to remember that this power applies also to the base. Sorry, adds also to the coefficient and to the variable. So it's 3 times 3 times 3 is 3 to the 3. So that all overall will give me the answer of 3 to the 3 is equal to 27 x to the 6. That's just a number. So to simplify it, just write it as a number. This is a variable, so there's no way to simplify that. It's just an x to the 6. Okay? Power of a power is okay? So power to a power means that the exponential terms has an exponent. These exponents must be multiplied. Here's an exponential term. It has another exponent. You multiply the exponents. When we raise anything to the 0, we always get 1. So there was some confusion about this when we first looked at this in class today. Let's take a look at why this is using our division rule again. So if I have a division problem like x to the 2 divided by x to the 2, what's that equal to?
1.
Why is that equal to 1?
This is the same top and bottom.
Yeah, because anything divided by itself is 1. But I have some restrictions here. X is not equal to 0. Okay. And that's from our last unit. We want to remember x is not equal to 0 here. 0 to the 0 is not necessarily 1. But x to the 2 over x to the 2, I could write this as x to the 2 minus 2. And that would be equal to x to the 0. 2 minus 2 is 0, so that's x to the 0. So that is equal to 1. So therefore, anything to the 0 is 1. Except for 0. 0 to the 0 is, we don't think about that. Okay, anything to the 0 is 1. And we can see that from our division rule. This is another example of when something is confusing. Look at a simpler example or something based on other things that you've already looked at. Like x squared divided by x squared. Everyone will tell me that's 1. It's the same thing divided by itself. All the x's cancel on the top and bottom, leaves 1. So here, x is not 0. X is 2 to the minus 2 minus 2. X to the 2 minus 2. 2 minus 2 is 0. X to the 0, 1. Okay. And then we've already looked at negative exponent laws. When an exponent term has a negative exponent, the reciprocal is used to provide a positive exponent. So the reciprocal means throw that thing, whatever this thing is, to the bottom of a fraction. The negative just means that belongs on the bottom of a fraction, please. That negative is just a set of instructions saying put that on the bottom of a fraction. Yes, Jackson?
We're building, each year we're building off of last year, we're just making it even bigger and bigger, right?
Yeah. Yeah. So this is all review, right? Is that what you're getting at? Yeah. And now we're going to put that into the context of exponential functions. And the things that we're adding are reciprocal exponents, and negative exponents are something that we certainly need to review if we didn't have them before. A negative exponent goes to the bottom of the fraction, right? Also, to the 0 means it's equal to 1. Yeah. Because that, like, anything to the 0 means divide that thing by itself. Or multiply it by itself 0 times is another way to think of it. So you always have 1 multiplied by whatever it is you're talking about. So 10 multiplied by itself 0 times is 1 multiplied by no tens. It's 1, right? So let's go back to our, if I zoom out here, I zoom one over here. Watch me struggle with the technology. And I climb back up here and we look again at our function over here. We had f of x is equal to 2 to the x, and we looked at positive values of x, and I cheekily drew on the negative portion of this graph. the domain of x is all real numbers. X could be negative and approaching negative infinity. X could be going to positive infinity. So what would be the value of this expression if x is equal to, let's say, negative 2? Someone solve this for me. What's 2 to the negative 2 now? 2 to the negative 2. I'm not getting a whole, like a forest of hands. What I'd love to see right now is a forest of hands all eager to tell me what 2 to the negative 2 is. So if we don't have a forest of hands, let's go through it step by step. Hands up, who's still a little confused? How do I do 2 to the negative 2? Rather than just cranking it on my calculator. People a little confused, or am I talking about something that everyone gets? No? Okay, let's take a look at it. The negative, what do I do when I see a negative exponent? If I want to evaluate that. Yes, I put it to the bottom of a fraction. So I have 1 over 2 to the 2. What's 2 to the 2? I have it over here. 4. So this is 1 over 4. 2 to the negative 2 is 0.25, if you like. 25 cents, 1 quarter. Okay? So over here, I should actually, this is not a very accurate drawing. It should be well down here. So let's plot some of these points. I'm just going to erase that. Oh, those points were good. And then I'm going to now graph it again. Here, we had these points, we had that point, and we had that point. So this comes down here like this. It starts now approaching the y-axis. It goes through the point 1/2. And I'm going to zoom right in here so that I can get these a little bit more accurately plotted. Here is x is negative 1 will give me the point 1/2. X is negative 2 gives me the point 1 quarter. X is negative 3 gives me the point 1/8. X is negative 4 gives me the point 1/16, 1 over 16. 1 over 32, 1 over 64. Will this ever touch the x-axis? No, the x-axis is an asymptote. It gets infinitely close to the x-axis, but it is not touching the x-axis through there. There. Okay, this is a line, but whatever. You get the idea. So that's how you would graph these exponential functions, and that's what we expect to happen with negative values of x, is it gets very, very close to the x-axis, but should never touch it. Okay. So now let me give you a walkthrough of the delta math for today. So here is the delta math assignment 3.1. I want to review transformations and the exponent laws with you. So here we go. Basic exponent rules. We'll give you questions like this. 3 to the 8 over 3 to the 3. What's that? This is 3 to the 5. Shiraj took 8 and he subtracted 3. That gave him 3 to the 5. Submit the answer. It will be correct. Yes, okay. New problem. So 4 to the 8 over 4 to the 5. Well, we know that. We just did one just like that. 2 to the 4 to the 2. What's that? What's this going to be? Yeah, to the 8. That's right. That was the correct number of fingers. This is 2 to the 8 because it's 4 times 2. Let's see the nice things that delta math gives us. Expand it. This is method 1. So expand means figure it out using simpler exponent laws. 2 to the 2, 2 to the 4 to the 2. Expand that as a multiplication. 2 to the 4 times 2 to the 4. And then write that out. It's 2 times itself 8 times. Collect all those. It gives you 2 to the 8. Method number 2 is the shortcut. Multiply the powers. X to the A to the B is X to the A times B. Cool. This is great. Read this stuff. Review it every time. Let it sink into your brain. The basic exponent rules there. I want you to do several of those problems. They're very fast. Mixed power problems. Now, let's take some problems like this and start answering those. So, if I have to use some scrap paper for these, that's fine. I want to be able to answer these types of questions. So, let's go get ourselves some space. Here we go. I have an infinite whiteboard here. So first thing I might do is copy this out. Negative 9y to the 5 times minus 4 x to the 5 times y. All right. So here I need to apply some exponent laws, and I need to ultimately simplify this to a single line. I want to observe bedmas, so if I had something like that, I would have to do this exponent first. If I had operations to do inside this bracket, I would do them first. But I don't. So that all I need to do is now this multiplication of this times this. So, first of all, what's going to be my x to the power of in the final answer? Yeah, x to the 5. Just shout it out at me. How about my y to the power? What will be my y to the power? 6, because this is y to the 1. And I'm multiplying y to the 1 times y to the 5 gives me y to the 6. And then what's my coefficient? Positive 36. Because I have negative 9 times negative 4 gives me 36. Great. So that there is the final answer. So I can put that in there. It's 36x to the 5 y. Oop, and then you want to push your little arrow over so you don't make your y an exponent. Y to the 6. Submit answer. Yes. Yay. And then go through and take a look at how they talk about it. They do first multiply the numbers. Cool. Then they say there's the only power of x, so there you go. And then y to the 5 times y is y to the 6. That's y to the 5 times itself one more time. That's y to the 1. I'm 41 to the 1 years old. And so there you go. That's how you do it. All right. And so then we're going to get other problems like this, where here, can people look at that now and just tell me the answer? Using only positive exponents, I've been asked to do this. So what's that going to be? Siraj?
5y3 over x.
5y3 over x is perfect. That's right. It's 5x to the negative 1, y to the 3. But they want only positive exponents. Okay, so if I write this one out, and I want to do that, I divide the numbers by each other. So 125 divided by 25. That's where Siraj got 5. And then x to the 3 over x to the 4 will give me x to the 3 minus 4, which is x to the negative 1. Or I can just cancel these and cancel that and leave 1x on the bottom, however you like to do it. And then y to the 5 over y to the 2. So that's equal to 5, the product of this, x to the 3 minus 4, x to the minus 1, y to the 3. Okay, this is equal to 5y3, as Siraj said, over x. Because that x to the negative 1 just puts it on the bottom of the fraction. Cool. So go ahead and put that in. Oops. 5y to the 3 over x. Submit answer. Yes. Hooray. And then take a look at their solution. Your goal today, your learning goal is to sink these exponent laws into your brain so that the unit goes smoothly. So that's why I'm giving you lots of problems to practice here. Okay. Next we're going to look at function transformations, okay? So now we're reviewing. All right, now we're looking at a quadratic function. It's y equals f of x. It's some quadratic. It has a vertex of negative 6, 6. Where will the vertex be if I apply this transformation to it? So this is f to the x minus 2. Where will that vertex be? Oh, how do I zoom in here? I'll just do plus here. Plus. There. Now I think people can read. So where will this vertex map to if I apply this transformation? Someone tell me what this transformation is going to do to g of x. Where is g of x going to be relative to f of x? Siraj.
2 to the right.
This will move it 2 to the right. This is a set of instructions saying subtract 2 from all your inputs. That moves it 2 in the positive direction x. So in the video, I'll go that way. Yeah, so that's going to move this 2 to the right. Here is my x value. What will be my new x value of this parabola? Negative 4. Very good. Yeah, so this is negative 4, 6 will be the new location. And then use delta math to review this idea. Correct. Draw a sketch of the potential graph. Here's the potential graph of f of x. It's a parabola with that vertex. Or it says you could just plot the vertex. And you could plot it in your brain if you can visualize this. And then you see g of x is equal to fx minus 2. This is subtract from inputs. This is a d value transformation. Fx plus a shifts opposite, they remind us. Shift right 2 units. So we want to get a lot of practices shifting these points. New problem. Here is a trickier one. I have the vertex of a parabola is negative 5, 3. And I'm going to, what are these things telling me to do? I know you've got it. Everyone's relying on Siraj to answer these questions, but I want everyone to be able to answer these questions. Brody, can you read this question from the back?
I can read the top part, but the top part. Okay. Quadratic function y equals f to the c, fx.
Okay.
Is plotted on the graph and the vertex of the resulting parabola is negative 5, 3.
Mm-hmm.
What is the vertex of the function defined as g of x equals f of x minus 3 minus 5?
Good.
Yeah.
So I want to be able to sketch in my head or quickly sketch on a piece of graph paper that point, negative 5, 3. That's the interesting point. It's negative 5, 3. It's right there. Negative 5, 3, okay? And that's the vertex of some parabola. Then I'm going to transform that parabola with these two transformations. What does this transformation do to that point? Negative 5, 3. This one is moving it left and right because it's connected to an input.
So moving it right 3.
That's right. That's going to move it right 3. So it's going to move it to negative 2. And then what's this do to it? That says subtract 5 from all outputs. 3 was the output.
Down 5.
Down 5. So now it's at what point? Now this is at the point negative 2, negative 2. Because I took negative 5 and I moved that to the right 3. So that's now at negative 2. And then I took this point 3, at y value 3, and I moved it down 5. So now it's at negative 2. Negative 2, negative 2. Submit answer. Yeah, so that's good. So draw a sketch. So we did that. Cool. And then it says shift right 3 units. We remember if we add to inputs, we have to go opposite direction of what the sign is saying. And then if we add or subtract from outputs, we do exactly that. So that shifts down. F to the x plus a shifts up or down. So there we go. Now it's at negative 2, negative 2. Okay? So that's how we apply those transformations. If we keep going, we're always just getting translations here, and that's fine. We get a good practice with our translations. Okay. So we did some translate functions practice. With this practice here we have, they're giving us exponential functions in this practice. Now we've seen some exponential functions, and we want to translate this 4 units up. The way the delta math interface works, if I grab the blue points, it's a stretch transformation. I don't want that. I don't want to stretch this or reflect it. I'm not doing those stretches and reflections, although this is a cool way to think about what stretches and reflections look like for exponential functions. Okay, so I'm going to put that back to where I found it. And then the green one is how I do translations. So here I know that, I have 2 to the x. That's this function. It looks like the table of values we already looked at, and I want that to go up 4. So let's grab this, and we'll move it up 4. And that would be, yes, submit the answer, yes. Yes, that's correct. This means shift up 4 units. So there it is, shifted up 4 units. There you go. That's how we do these types of problems. And so here we're going to be shifting to the right 1 unit and over 3 units. So grab the green one. Right 3 unit and up 3 units. Let's see, did I get the numbers right? Yes. Right 1 and up 3. Submit answer. I give you a lot of problems like this to do because I want you to get lots of practice. And then we're going to look at stretching and compressing functions. Here's the absolute value function, one of our old friends. We want to what's this function transformation doing? Austin, tell me about this function transformation.
Like, tell you what.
Well, what's this 1 over 4 doing? You could tell me, is that an A, a K, a C, or a D? Or you could describe the transformation that would do.
That's like you rise or run, so we'll go 1 up, 4 across.
Yeah, kind of. Yeah, it would be 1 up, 4 across. There. Yeah. It squishes the function by a factor 4. It's squeezing it by factor 4 in the y-axis. That's an A transformation. That's multiplying my outputs, and it's by a factor 1/4. So I took this 0.44 and made it the 0.41. Shrink the y's by a factor 4. Submit answer. Yes. Hooray! So we look down here. This is a vertical dilation of 1/4. You can think of your eyes dilating as you get the math problems right. You're so pleased with yourself. Okay, so that's how you do these ones. And then transform functions mixed. Okay, here I'm going to do y is equal to the negative absolute value of x. Now, someone back corner, from Jared back. Someone tell me what this negative is going to do as I transform the absolute value of x function. What's that going to do? Flip it? Yeah. In the y-axis or in the x-axis? Yeah, right. This flips it in the x-axis. So if I take this 0.44, I can move that to the 0.4, -4. There we go. And that's been reflected in the x-axis. Notice that reflecting in the y-axis is uninteresting for the absolute value function, unless I already had it translated or something, in which case the whole thing would reflect over. So there we go. And you can also notice the 0.00 stayed the same, because that's indifferent to being flipped. It's still there. So practice all these, get used to all of these. And then the last thing, identifying inverses graphically. So here is a function. I want to find the inverse of this function. How do I find the inverse of functions? That's right, Dave. I flipped the y and the x. So where will this point here, -5, 3, where will that go?
3, -5.
Right, let's take that away. So if I go to 3, -5, that'll be 1 point. That's this one reflecting through this line over here. We need to plot at least 5 points. So here, can I plot that point? Why can I plot that point? It stays the same. It reflects to itself. If the function touches the line y equals x, that point will also be on the inverse. Because it's like you're touching your nose to the mirror. Your reflection's in the same place as your nose. Okay, so then I have also this point -2, 2. So that goes to the point 2, -2. So over here. And then another point I could find is -8, 4. So that will go to the point 4, -8. And now I can kind of see, oh, this is going to be a line with slope -3. So I could also put this up here. There. Let's say that that's the reflection. Submit answer. Yes, I'm sure. Yay! Graph the inverse of the provided graph on the accompanying set of axes. The inverse. Switch the x and y. So they said go ahead and find 5 points that are on the function, flip the x's and y's and plot them. You'll need some practice doing that. That way you'll be able to find your water slide if the wind blows it over and pushes it into your swimming pool. Okay, so I hope that your math practice is fruitful today. Definitely find me if you have any questions.